Today we formally start chapter 3, which is about fields. Now, to be fair, we've been talking about fields for longer. Last week we also talked about the subject. There's a natural overlap in these subjects, right? So as you recall, when m is a prime number and you reduce the integers mod m, what you obtain is a field. And that basically means that every number is invertible, except 0, because 0 is never invertible, right? Everything times 0 is 0, so there's no hope of ever getting 0 times something to be equal 1. So all the other numbers are invertible in the field. Now, in the case of modular arithmetic, this means that if you have a number that is not divisible by m, in other words, it is different from 0 mod m, then you can always find its inverse, which we in this example is called b, right? So some number that would multiply times a gives you 1. And this is important because this tells you how to solve all these linear congruences as we've been seeing so far. So let me, as a reminder, give you an example that we've talked about in the past. And I have two examples here for you. The one on the left is the multiplication table mod 12, so the clock, the very first example I talked about. And the one on the right is the multiplication table mod 13. 13, as you know, is a prime number, so the one on the right is a table that corresponds to a field. The one on the left isn't, right? And you can easily verify this. You already know in general how to find the elements that are invertible, mod m. It's those that are coprime with m, in other words, those that share no common divisor. And this is an if and only if condition. As you can see here on the left side, if you check all the divisors of 12, there will never be a number 1 on those rows, right? Because those are divisors of 12. Also this one, by the way. But it's not just the divisors of 12. Any number that shares a divisor, such as 8 and 9, will never have a number 1 in their row because they are not invertible according to the theorem I'm talking about, right? What other examples do we have? 10 is also an even number, so all the even numbers have no hope of being coprime. Now 11 is consecutive with 12, so that one is always coprime, always invertible, and the inverse is actually easy to find because 11, or in general m minus 1, is always its own inverse. The same is the case with 1. 1 is always its own inverse, right? So this is true in general for every modular class. 1 and minus 1 always are invertible and they're their own inverses, right? But these are not the only ones. So for example, the row number 5, if you go along it, you'll eventually hit a number 1. And we know this is true. This has to be true because 5 is coprime with 12. In this case, and this is more or less a coincidence, 5 happens to be its own inverse, right? The number 7 is also coprime because it is prime and it's not a divisor of 12. So if we look at the 7th row and we move from left to right, eventually we'll always hit a number 1. And in this case, it happens to be its own inverse as well. This is again more or less a coincidence, or at least as far as what I'm trying to, the point I'm trying to get across, it is. Now, what other number? Did I skip something? I think that's everything, right? So in general, when you are scanning for a row to find a number 1, whenever you hit a number 1, the column is the inverse of that row, right? Now, if you look at the table on the right, mod 13, 13 is prime, so we expect every row to contain exactly one number 1, and as we saw last lecture, this happens if and only if every row contains exactly every single number, but shuffled. Now, we didn't really prove that last bit, so I will do that now. Let me see if I can find all the number 1s here. As you can see, every single row, of course, except 0, because that one consists of just the number 0, contains a number 1. And if you look at the rows, each row contains all the numbers shuffled, all the numbers in a different order, but there's no repetition, and every number appears somewhere on each row. So there's something clearly special about prime numbers, and Part of all of this is something that you're tasked with proving as part of the problem set. But now, the observation I care about is that every row mod p, mod a prime number, contains all numbers with no repetitions. So let's prove this formally, because from here we will derive a very interesting result, which is arguably the first non-trivial result about number theory, and also the last major theorem that we will look at for this particular chapter about modular arithmetic. And we can look at more results later. Like I said, the last chapter we still have some freedom of what we want to do. But anyway, let's try formalizing this idea. And as you'll see, the proof is very easy. Sometimes how you formalize things, how you write things down in a precise language is half the problem of figuring things out, right? So let's maybe call this a lemma. And the lemma is, of course, what I want to say is that suppose P is prime or M is prime, let's call this P. And we pick a row, right? So let's say that A is a row and we want this row to be non-zero. So let's pick a number between A and P, right? There's only P minus 1 rows, so excluding 0. So what is my claim, right? For I, let's index the rows. So of course I don't care about the 0th row. So we have ij smaller than p. If ia, right? So this is the ith row is congruent mod p to ja, then I is equal to j. So in words, the row A has no repetition. Right? Does this make sense? So the row A, for example, here when A is equal to 7, what is the row A? Well, it's all the multiples of A, right? But we only care about the columns. How many columns do we have? We have P minus 1 columns, except 0, of course. So it's 1 times A, 2 times A, 3 times A, and so on. And to claim that these have no repetitions, it means that on the table, meaning mod P, they can only be equal if they have the same index, right? So this is what the lemma is saying, just in slightly different words. Another way of interpreting this that is also kind of useful is that if you take the multiples of A, so 1 times A, 2 times A, 3 times A, and so on, and the last multiple is, of course, P minus 1 times A, because P times A is already 0, right? And that's the first row, the one we don't care about. Now, this is an abuse of language, because what this means is that everyone probably understands what this means, but I didn't properly define it, right? So let me call this is an abuse of language. And you will see this commonly. It basically means I won't bother defining this because it is clear from context, but it isn't properly written, right? This symbol, the 3 parallel lines, is a symbol that I defined between two integers, a relation between two integers. But here I'm comparing two sets, which isn't exactly isn't precise, right? So just be careful about this. But I think you can all see where I'm going with this, right? So what I'm saying is this is the row, this is the row A written in order left to right as it appears on the multiplication table. And the claim I'm trying to make is that these are just all the numbers, but shuffled, right? So this is why I'm writing these as sets. They might be in a different order, and I do have to reduce the mod p, but I think this is clear from context, right? So this is all numbers shuffled, right? Two sets are equal, and the order doesn't matter in the set. So this is what I'm saying. Shuffles. Maybe I'm being too adding too many details and you already know what I'm talking about, but hopefully this helps clarify what I'm saying. Let's prove the lemma. The ideas for the proof are already contained in things we've seen in the past, but let's just for the sake of formality and completeness do it. Okay, so suppose everything that the lemma says, and let's just worry about proving that I is equal to j. So since IA is congruent to this, that means by definition that P divides the difference between these two things. And from here, I can comfortably factor out A, right? I haven't really done anything. This is just the definition. Now, by Euclid's lemma, here we use the fact that P is prime. So if P is not prime, I cannot conclude this. So obviously P being prime is very important. And you can easily see in the example with the clock mod 12 that if P isn't prime, such as here, this isn't true at all, right? In fact, there's rows that have a lot of repetitions. Let me see if I can quickly find, for example, the row number 4 just contains 0, 4, and 8 and no other numbers, and they repeat a bunch of times. They repeat 3 times, right? Sorry, 4 times. Okay, let's continue. Now, by Euclid, P must divide A, or P must divide I minus J. But P cannot divide A because A was chosen as a non-zero row, right? So this one does not happen. This one does not happen. So P actually does divide I minus J, right? But these are all positive, presumably positive numbers. And actually, now that I think about it, there might be a slightly better way of writing this. So, okay. Let me add one condition that really doesn't matter at all. But if you look at this hypothesis, instead of writing it this way, where I and j can be any two rows, let's just assume that these are ordered already, right? Because one of the rows comes first and the other one comes later. So why don't I just write them in order? This is what I'm saying. This is j and then comes I, right? I can assume that this happens because one of them will be first, the other one will be later or equal, right? So let's just assume that they're ordered that way. This is just for the sake of simplicity so that this is a non-negative number. Okay, so either if P divides I minus J, that means that either this is 0 because everything divides 0, or both are positive, are natural numbers, positive naturals, I would say. Positive integers, and okay, before I look at the chat, let me just finish writing this. So P is less than or equal to I minus J, but this is impossible. Because I and j are both positive numbers smaller than p. And this is an argument that we've used when we proved the QR formula, specifically the uniqueness. Okay, so the question is, what does the red line mean? I'm simply ruling out this possibility, right? So maybe I can add this more this detail. But this cannot happen, right? But this cannot happen, therefore P must divide I minus J. And then we have two more possibilities, which is that either I minus J is 0, or both of them are positive integers. But then we have this this implication, right? That if something divides something, then the first something is less than or equal to the second something, because they're both positive. So P must be less than or equal to I minus J. But this is impossible because I minus J is literally the difference or the distance between I and J. I and j are two numbers between 0 and p, so the distance between them cannot be bigger than p, right? And this is the same argument that we use for the quotient remainder formula or the division algorithm. Okay, so therefore, the only possibility that remains is that I minus j is 0, or in other words, I is equal to j, right? And this proves the lemma. Any questions about this? And this is called a lemma because with this I'm going to prove a very important theorem that is known as Fermat's theorem. And again, this is probably the first theorem that is not evident at all. You cannot, I mean, it's also not hard to prove, but it seems like this requires an additional insight beyond just, playing around with modular classes. I mean, you could argue that the Chinese remainder theorem is also non-trivial, but people who are used to working with this probably don't find that one as mysterious as this one. This one is actually quite clever. And there are generalizations of this, and if you've taken this course in the past, you know those exist, but you probably didn't cover them in a lot of detail. So in my opinion, it's not worth covering them in a superficial way, so that's why I'm just going to talk about Fermat's theorem. So the statement is as follows. Suppose A is non-zero, so P does not divide A, then A to the P minus 1, mod P is prime obviously, has to be 1, right? If you multiply A on both sides, what you get, I will write this and then erase it. You get this, right? And that is true even if P does divide A, because 0 to the P is actually equal to 0, right? So these are equivalent forms of the same theorem, and you might find this in a textbook, which is it looks a little bit more general, but it's of course the same argument. Okay, so let me prove this one, which is the harder one to prove. Let's prove this using, of course, we'll use the lemma, and you'll see that this is very, very clever. So what is a to the p minus 1 power? Well, this is a times a times a p minus 1 times, right? Now this is the same, this is congruent mod p to the product of all these a's, but I will do something very clever. So instead of considering just the numbers a, I will consider the multiples of a, right? So for that, I will say 1 times a, 2 times a, 3 times a, so on, all the way to p minus 1 times a. Now here I am multiplying all of this times p minus 1 factorial. So I have to compensate for that. And how do I compensate for that? Well, if you think about this, p minus 1 factorial, okay, maybe there's a better way of writing this. So let's do this in 2 steps, and maybe this becomes a bit more apparent. So what is this number right here? Let's do this in 2 extra steps. So according to the lemma, this is by the lemma, right? If I multiply all the multiples of a, which is a non-zero row of the multiplication table, mod p, then this is just, if you look at the part in green, this is just the numbers shuffled, right? And when I have the numbers shuffled, the a disappears. So this is just 1 times 2 times 3, all the way to p minus 1. Which is equal to p minus 1 factorial if I write this in a more succinct way, right? Okay. But on the other hand, what's happening? On the other hand, this I can simply move the p minus 1 factorial to the other side. Hopefully this is clear. Actually, I don't need this anymore. So this is the same as p minus 1 factorial times a to the p minus 1. Those are equal, right? Not just congruent, but actually equal. So now p minus 1 factorial is invertible. And this is because 0 is not an element of those numbers, right? If you multiply everything 1, 2, 3, 4, 5, all the way to p minus 1, those are all non-zero, and p is prime. So this is a field. That means that all that number, whatever it is invertible. Now there's another result that we could have used, which we won't really prove, even though the proof isn't that complicated either, which is known as Wilson's theorem. Says that that number is not just invertible, but it is actually just minus 1. But we don't really care about that. So we cancel it. Cancel it on both sides. Right? I don't care what the inverse is, even though I could figure that out, but I won't. I don't care what the inverse is. The point is I can just divide it on both sides or multiply the inverse on both sides. And what I have left is p minus 8 to the p minus 1 on one side. And if you want to add a 1 here, then this is just 1. Right? And that's how you prove Fermat's theorem. And as you see, the key insight is the fact that rows don't repeat themselves. It's the fact that every row has every number shuffled. Because if you multiply, this is basically, so by this I mean this right here is you multiply the entire row together. What happens if you multiply a row together? Well, it should just be all the numbers multiplied together because the numbers shuffled and the order doesn't matter when you're multiplying things, right? So you can cancel out this p minus 1 factorial, this product of all numbers, and this is how you get the a. Okay, so the question in the chat is why would the first line of the congruency hold? By first line, do you mean this one? Why is that equal? The second one, so this one? Okay, so that one follows from the lemma, right? If you look at the lemma says two things. The lemma says that if you take the row corresponding to the number a, and you take all the multiples of a, so the row, right? The multiplication row of a, then that is the same mod p as just the numbers 1, 2, 3, 4, all the way to p minus 1. There's no a on the right side. A doesn't play a role because when p is a prime number, the multiples of any non-zero number are just all the numbers, right? So a doesn't appear here, as you can see. If you look on the right side, there's no a here. But of course, a appears here because it is the row of a. So in other words, if you maybe it is clearer if you look at this again in the row. Let's say that you're fixated on the number 6, right? I want to multiply all the numbers in the row number 6. So all of these numbers. Of course, I have to exclude 0 because that doesn't make any sense. It will just be 0, right? So what happens if you multiply those numbers together? That's the multiples of 6 mod 13. If you look at it carefully, you'll see it's just the numbers 1 right here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. It's all numbers, but maybe in a different order. But when multiplying it, it doesn't matter. So it didn't matter that this was the 6th row. All that mattered is that it's all numbers shuffled, right? So the same thing happens here. If I'm multiplying the multiples, sounds kind of weird, but if I multiply the multiples of any number a, it's the same mod p as multiplying all the numbers, right? And the rest is not even a congruence, it's just equal signs. So those should be more clearer. How did we cancel p minus 1 factorial? So p minus 1 factorial is definitely not 0, right? Because 0 is not a factor of that product. So p minus 1 factorial is non-zero, therefore it is invertible, and I can just cancel it on both sides. I don't really care what the inverse is, even though I could figure that out if I had like an additional lecture to spend on this, I could actually tell you explicitly what the inverse is of p minus 1 factorial. It is -1. But that doesn't matter. That doesn't matter. Because if it is invertible, it means that there is an inverse, so you multiply it on both sides, they cancel out, and what you are left with is a to the p minus 1 on the left side, and just 1 on the right side, right? So you have this on the left side, and this on the right side. P minus 1 factorial is definitely invertible. Yes, you're welcome. Let me fix the notes a little bit, so that it's still readable. There we go. So this is Fermat's little theorem. Now you might be wondering, why do we care about this? It seems like this is just a curious fact. Okay, an intuitive explanation for that. Of course, so the intuitive explanation is the one that I just mentioned with the rows, right? The point is that whenever you fix a row, this is mod a prime number. You fix a row and you want to multiply the entire row together. The key insight that Fermat came up with is that it doesn't matter which row you're on, you're always multiplying the same numbers together, which is all of them, right? Again, this is just 1, 2, 3, 4, 5, and so on. You have all the numbers in a possibly different order. So every single row, so this is A equals 4, A equals 8, all these rows give you the same product, right? A doesn't play any role. So A to the P minus 1 is always just 1. It's the same thing. It's the same number. So my suggestion is you can try to do this in a more explicit example, right? Just pick a number P like I just did, 13, and then pick a particular number A, and notice that all the rows is just the numbers shuffled, and when you multiply them, well, you get this equality or congruence. Maybe if I write some examples, this becomes even more intuitive. So let me tell you why this is useful. So we've already seen how we can simplify tasks using modular arithmetic, but there are drawbacks, right? So what happens if you want to multiply, for example, 50 to the 247, and you want to reduce this mod 83, right? 83 is prime, by the way. So this seems difficult because, for example, if I were trying to calculate 82 to a really large number, mod 83, I can just substitute that for -1 and get something really easy. Or if I were trying to multiply, say, 85, then this is still 2 to the 247, which seems easier. But 50 is kind of like right in the middle, right? It's far away from the negative numbers. It's far away from being something slightly above 83. So 50 doesn't simplify at all mod 53. And like I said, the exponents are tricky. But I just gave you a magic rule to simplify all the exponents whenever you have a prime number. If it's not prime, then this would take more work. And this is not something that we won't be covering in this class, in this lecture. Right. So how do you do this? Well, divide. So this is a question, right? So divide the exponent 247, and you divide it by 83. So I already came prepared, and I know, sorry, by 82. My apologies, 82. So I already know that this leaves a remainder of 1, right? And then 50 to the 247 is equal to 50 to the 82 times 3 plus 1, which is equal to 50 to the 82 to the 3 times 50. These are just exponent rules, right? There's no modular arithmetic, no trick here. And now I reduce this mod, this prime number, 83. And if I apply Fermat's little theorem, we know that 50 to the 82 is just 1. So this is 1 to the third power times 50, which is, of course, equal to 50. So I have this horrible, complicated number on the left side, and I managed to reduce it to something really manageable using Fermat's little theorem. If we don't use Fermat's little theorem, we don't really know how to reduce exponent numbers, right? The powers. So this is one example. In general, of course, we can do this. This works in a lot more generality, right? So if K is congruent to L mod P minus 1, P is prime, then A to the K is congruent mod P to A to the L. And this is the rule that we're using, but in a more general setting. In other words, if you are trying to work with a problem of the form A to the K mod P, and you're trying to compute that, you can always reduce the exponent K mod P minus 1, as I just did in the above line, right? All I did was reduce 247 mod P minus 1, which is equal to 1. So this is the same thing. And proving this in more generality is a very, very good exercise. It is not difficult. It doesn't require anything that I haven't mentioned explicitly. It's just applying the QR formula to K and L, right? And see what you get. So this isn't difficult, but this is for example a really good candidate for something to be on a test or something like that. Because it will test your understanding of not just Fermat theorem, but a little bit about prime numbers and the division algorithm. It's like a combination of several things. So here's one example that will hopefully give you intuition. There's other things that you can say about consequences. So corollaries of Fermat's theorem, just some important consequences that might be useful. So the inverse. The inverse of A is always A to the P minus 2. Okay, and for this, actually, this isn't true. I need to add a condition. So if P is not 2, right? So P is prime, but P2 equals 2 is kind of like a weird case because it's the only even prime. So here, things don't really work out. So this is the first corollary. So the inverse of A is always A to the P minus 2. Why? Because if you multiply those two together, A and A to the P minus 2, you get A to the P minus 1, which is 1 according to Fermat's theorem, right? So if you multiply two things and it gives you 1, that means those two things are inverses of each other. Now this is cool. It might seem useful. It's not that useful because A to the P minus 2 is generally harder to compute than computing the inverse using, say, the extended Euclidean algorithm. But it might be faster in some computational applications of this. Yeah, so that's one way you can find the inverse mod of prime number. Another one that I find very intriguing is that so what happens if you take A to the P minus 1 divided by 2? Dividing by 2 makes sense because P is bigger than 2, right? So this is always an odd number, so P minus 1 is always an even number. So what happens if you take this number and you square it? Well, this is just A to the P minus 1, which according to Fermat's little theorem, mod P is 1. In other words, I found a number that when I square it, I always get 1. So doesn't this mean that A to the P minus 1 over 2 is like the square root is like a square root of 1? And this is a slightly harder exercise, which you can also attempt to prove, is that A to the P minus 1 can only be plus or minus 1 mod P. And if you want to hint, use Euclid again. This isn't obvious at all. If I scroll up to the multiplication table mod 12, you can see that there's a bunch of 1s on the diagonal. 5 squared is 1 mod 12. So the square root of 1 is 5, but it is also 7, and it is also 1, and it is also minus 1. So the number 1 mod 12 has a bunch of square roots, a bunch of numbers whose square is 1. So it isn't obvious at all, even though it might seem, because in the real numbers, of course, it is obvious that the only square root of 1 is plus minus 1. But when you don't have a field, it isn't obvious that this is true. So you can try verifying this. If you have a number whose square is 1, then that number has to be plus or minus 1 mod prime number. So this is another property of fields that is not true in general, and I just gave you a counterexample, right? So the square root of 1 mod 12 is actually a bunch of different things. 5 and 7 also act like square roots of 1, even though they're certainly very different, right? So there's a lot of theory about quadratic residues, as they're called, or square roots, and we won't be covering too much of that, but there's some very challenging problems in the problem set, additional problems that are not marked, if you want to take a look at those. But yeah, there's a big part of number theory that is dedicated to studying, squaring, what happens when you square things, and when do you have a square root. So this isn't necessarily obvious. It's like a glimpse to more difficult things. Now, before we wrap up, I just want to give you one definition so that you can use it in the tutorial later, because you will be proving a few things about that. Next Thursday, so the next lecture, we will be constructing the rationals, finishing the construction of the rationals, and giving the construction of the real numbers. Now, the construction of the real numbers is kind of a conceptual jump. So we constructed the integers, we constructed modular classes. Right now, I will tell you how to construct the rationals, but constructing the reals is like considerably harder, right? So we'll spend the 2 hours of next lecture doing that. So let me just introduce the rationals to you. And it's the same idea as I did for the integers, right? So the motivation for the rationals is, of course, I want a field, but I don't want a field that is obtained by cutting the integers into smaller things like ZP, which is useful in its own sense. But I would like a field that is bigger than the integers, not just smaller, but bigger. So it has to contain the integers. It's in a way, it's what happens if you take the integers and you want to close it and take all the essentially, it's the smallest field, right, that contains the integers. So a fraction or a quotient, a fraction is a pair, let's say a comma b, where the first element is an integer and the second element is an integer, but it's not 0, as you might expect. And you will see in a second why it's important that this is not 0. Sorry, I usually underline the definitions. Okay, and we will define the following relation on fractions. So define. So remember, a fraction, this number, the same way that we did for the integers, this number here, this object, dreams with being a over b, right? In general, not just when b divides a, in which case it's just the quotient as given by the quotient remainder formula, but in general. So this number dreams of being a over b, and this number, this object, dreams with being c over d, right? We already did this for the integers, right? So if you find this confusing, then I suggest you look at that construction first, and then you look at this one. So how would you define two fractions being equal? Well, if I don't know anything about fractions, I can just multiply them out, right? The cross product, or whatever you call that in high school. So you have a times d, for example, a times d equals b times c. That's one way of defining this. And this makes sense because, of course, I know how to multiply integers, and I am not referring to any sort of division here, right? So this is perfectly well defined. And the remark that by now this is a routine argument, I won't even write this as an exercise, is that this is an equivalence relation, as you might expect, and it's an equivalence relation that is partitioning this weird product of the integers cross themselves non-zero, right? Using that, I can define what a rational number is. So a rational number is an equivalence class. Right? So you take any tuple, and then the equivalence class is what I call a rational number. And then the set of rational numbers is precisely what you get from taking all these fractions and reducing them mod this equivalence relation. Right? It's the set of all rational numbers. That's what Q is. Now, I need to tell you how to multiply, add rational numbers, what the order is, and how to embed the integers so that you indeed get an extension of the integers, right? So let's define the operations. Okay, so you have two rational numbers, and we need to include the representatives in this case. So we have this plus C, D. And how would we define this? So let me clarify, right? This is the one I'm defining. It's not that this is obvious. I'm defining this symbol, this plus symbol right here. And I'm also going to define to you the following product, CD. And with these two operations, you have everything you need to prove that the rationals are a field, which of course the integers are not. So there is something new to prove here. And it seemed like a long proof, but it's just chasing the definitions, right? There's nothing too obscure going on here. And it's one of those things that it might not be the most interesting thing in the world, but you have to do it once to understand why it works and how it works. So how do you think you would define the sum? This is slightly more complicated, more convoluted than with the integers, because of course these objects are supposed to be fractions, and I will eventually, of course, represent them by writing them as fractions. So what do you think this should be? How do you add two rational numbers together? And while you think about that, I'll tell you how to multiply them. Multiply fractions is easy, right? If the first object is supposed to be a over b, well, then this is just this, right? Just multiply them coordinate-wise. But the addition is the one that, funny enough, is more complicated. So how would we figure this out? Okay, someone is already... okay, someone gave the answer in the chat. Ismail, thank you. Okay. So yeah, and indeed, this is just the rule that you learned a long time ago. AD plus BC, and you take a common denominator, right? That's not the only way of defining it. Of course, this will be equivalent to a bunch of different things. Yes. Okay. Yes. Thank you. Right, so that's how we define those two things. Now, in this course, we've focused a lot on the algebraic properties of all these constructions. I haven't focused too much on the order. I think I did maybe explicitly tell you how to define the order in the integers. It's analogous defining the order in the rationals, and we will cover that in more detail next time as well. But just so you know, there's a lot more detail that we could have covered that we didn't, but of course this is a very broad subject. And my goal for this is for you to know that these constructions can be made and we can formalize them, but there's a lot more to be said. But we have to find a balance between finding those things that are too technical and tedious and those that will actually teach you something new about how these objects work, right? So this is how we define the rationals, how we construct the rationals from the integers. And the final thing that I want to tell you is that if what should we call this? N is an integer, then how could we make sense of this integer as a rational number, right? So we can take n and we can send it to the rational number that consists of n comma 1, right? Why does this make sense? Well, because of course this is a fraction and it's dreaming of being this which is, of course, what we would assume is just equal to n, right? So this function is injective, and as you can easily verify, it preserves everything. Preserves the operation and the order, which I haven't properly defined, but I will. Right? So the most important fact about this is that if you take the rational numbers, you take the sum and the product that I just defined, 4 rational numbers, then you need a number 0, and I think you can guess what that is, right? If you take 0 comma anything, let's say 1, and you take the number 1, and the number 1 can be anything, like anything of the form a cross a, right? But we might as well pick one representative that we're comfortable with, which is 1, 1. Then this acts as the identity, the multiplicative identity. And the theorem is that this is a field. It's not just a field, it's an ordered field, but I haven't quite told you what the order is. You will look at the order during the tutorial, but it is defined analogously to the way I defined it in the integers. So there's nothing tricky going on here. Okay, so this is the very first, the most basic definition about what a rational number is. There's of course a lot of things to prove about the rationals. For example, something that is not true in the integers that will be true in the rationals in terms of the order is that between any two rationals there is another rational strictly in between. That is not true for the integers. There is no integer between 2 and 3, but there's infinitely many rationals between any two rationals. So that is something that is different, right? The order is very, very different, even though this is also a linear order. Okay, so let's stop the recording here.